This video continues our exploration to gases and the gas laws. This one will be looking at the relationship between pressure and volume, and it probably is best to review a little bit. We will be using the kinetic molecular theory, which essentially states that gas properties are dependent upon the gases constantly moving. We make 6 assumptions. The first is that the gases have no volume. The second is that there is no interaction between gas molecules. They each think they are alone in the universe. The motion of the gas molecules is rapid and random and continues in a straight line until they collide with something. When they collide with something, the collisions are elastic, meaning no energy is lost. At the same temperature, the kinetic energy for any gas is the same as any other gas, but the speed is not, and the kinetic energy is directly proportional to the Kelvin temperature. So if you double the Kelvin temperature, you will double the kinetic energy. These assumptions do not depend upon the type of gas being discussed, or in other words, the gas laws are independent on the identity of the gas. Remember that pressure is the number of collisions of the gas molecules with the container walls per second. The more collisions per second, the higher the pressure. The fewer collisions per second, the lower the pressure. There are several things that will affect the collisions per second. The first is the size of the container, or the volume. The second is the speed of the molecules, which we measure as temperature. The third would be the number of particles, which we would measure as moles. In this video, we're going to discuss the relationship between pressure and volume. So imagine, if you will, a container that is 5 liters in size, is at 298 Kelvin, which happens to be 25 degrees Celsius, and there are 10 gas molecules. This will have some pressure. We'll use kilopascals this time as the unit, and so that pressure is X kilopascals. Then we halve the volume of the container. Since the temperature hasn't changed, the speed of the molecules hasn't changed, but the distance they have to travel is 1/2 what it was previously before it collides with the wall. That means the collisions per second will double, and since pressure is collisions per second, the pressure doubles, so now we have a pressure of 2x kilopascals, double what we had before. This relationship between pressure and volume is known as Boyle's law. This is providing we hold the temperature and the number of moles constant, and mathematically it is P1V1 equals P2V2, where 1 and 2 are 2 different sets of conditions. This is an inverse relationship. If the pressure goes up, the volume must go down, so the product remains constant. If the pressure goes down, the volume must go up. If the volume goes up, the pressure must go down. And if the volume goes down, the pressure must go up. Once again, the product has to stay the same. So here is an application of Boyle's law. Suppose you have a 10-liter piston of helium gas with a pressure of 3.80 atmospheres. The piston is then compressed until the volume is 6 liters. What's the new pressure? We will be keeping the temperature and the number of moles constant. We know that the volume is decreasing, so the final pressure must be higher, since we are dealing with an inverse relationship. We know the starting values for P1 and V1 at 3.80 atmospheres and 10 liters respectively. We don't know P2, so we leave that as P2, and the second volume is 6 liters. We know that we have P1V1 equals P2V2, so now we plug in the values. We divide both sides by 6.0 liters. Notice the liters cancel out, and this allows us to isolate P2, and when you do the calculations, you get that the second pressure must be 6.33 atmospheres. With the new pressure being 6.33 atmospheres, you have to say, does the answer make sense? And yes, it does. We have a smaller volume, so the pressure must be higher. Everything looks good. So here is one for you to try. You've got some hydrogen cyanide gas in a 25-liter balloon. The pressure at this point is 935.33 kilopascals. Then the size of the balloon is altered so that the new pressure is 359.75 kilopascals. We're not changing the temperature or the number of moles. What is the new volume of the balloon? Stop, calculate it, come back and check your answer. And the correct answer is 65.0 liters. How did we get this? Well, we know that P1 is 935.33 kilopascals, V1 is 25 liters. We know P2 is 359.75 kilopascals. We are looking for V2. We have Boyle's law. Plug in the values. Divide both sides by 359.75 kilopascals. Once again, notice the units cancel and you're left with liters, which is the unit you're looking for, and you get 65 liters. Does that answer make sense? Yes. The pressure went down, so the volume must have increased. One last one for you. 135 milliliters of oxygen is compressed to a volume of 43.5 milliliters. The initial pressure was 948.72 torr. We're going to hold the temperature and the number of moles constant. So what's the new pressure in atmospheres? Stop the video, figure it out, come back and check your answer. Go. And the correct answer is 3.87 atmospheres. How did we get this? Well, we know P1, V1, and V2. But we don't know P2, so we leave that as P2. We know Boyle's law. We plug in the values. We rearrange. When we do this, we get 2,944.30 torr. So we can say that's the new pressure, except that the question says, what is the answer in atmospheres? So now you need to convert from torr to atmospheres. We know that 760 torr equals 1 atmosphere. So we take the 2,944.30 torr, multiply it by 1 atmosphere, divide by 760 torr, and we get 3.87 atmosphere. So a quick review of this. Remember that pressure is collisions per second of the gas molecules that contain a wall. If you hold the temperature and the number of moles constant, then increasing the volume will decrease the pressure. Decreasing the volume will increase the pressure. Increasing the pressure means the volume must be smaller. Decreasing pressure means the volume must be larger. This means that pressure and volume are inversely related. This is called Boyle's law. Mathematically, it's P1V1 equals P2V2. And this is when, as we say, N moles and T Kelvin temperature are held constant. We'll move on into the next video to look at another way to alter pressure.